Welcome to the deep dive. Today, our mission is pretty ambitious. We're going to journey across the entire expanse of cosmic history.
All at once.
All at once. We're looking at the very first objects flickering on at the cosmic dawn, and at the same time, we're watching galaxies die right next door.
It's a huge undertaking.
Right.
And the source material we're digging into, it's coming from JWST, from Hubble.
The heavy hitters.
Exactly. And they're giving us these profound and often, paradoxical insights. We're also leaning on some cutting-edge simulations to make sense of it all.
So we've really got two big themes today. First, this quest to finally find the universe's first stars.
Right. We're talking about population 3 stars, but also this other, much more radical idea.
Dark stars.
Supermassive dark stars. Yeah.
And then for our second theme, we're dissecting how galaxies actually die, this process called quenching.
Specifically how a huge galaxy like Andromeda basically starves its smaller neighbors to death.
Yeah. And what's so fascinating is this thread of contradiction running through all of it. JWST is seeing things that, according to our standard model, well, they just shouldn't be there yet.
They're too big, too bright, too early. It doesn't fit.
And then here, in our own backyard, the way satellite galaxies die is proving to be so much more complicated than our best simulations predicted.
It seems the universe, both in its infancy and its old age, just loves to defy our neat little boxes.
Okay, so let's start at the very beginning. As far back as we can possibly see, the cosmic dawn.
Right. So when we say cosmic dawn, what we're really talking about is the epoch of reionization.
The lights turning on.
Exactly.
Yeah.
Before that, for the first few 100 million years, the universe was just this dark, neutral fog of hydrogen and helium.
And JWST is our tool for piercing that fog, because the light from back then has been stretched so far by the expansion of the universe.
It's been redshifted way, way into the infrared.
Which is exactly where JWST lives.
It's what it was built for. And the revolution was immediate. They found Jade's GS-Z140.
The new record holder for the most distant galaxy.
The most distant confirmed galaxy, yeah. It was there just 290 million years after the Big Bang. That's a redshift of 14.32. It's just mind-boggling.
Okay, so you said this galaxy is a problem, an anomaly. Why is it such a headache for the models?
Because it's huge. It's surprisingly bright, incredibly massive, and physically large for that point in time.
How large are we talking?
Over 1,600 light years across. And its mass is already hundreds of millions of times the mass of our sun.
And our standard model, Lambda CDM, says that just shouldn't be possible so early on.
Right. In that model, things grow hierarchically. Little things merge to make slightly bigger things, and so on. It takes time.
So 290 million years is just not enough time to build up that much stuff through mergers.
Precisely. You either need star formation to be wildly more efficient than we thought, or the initial seeds of structure in the universe were much lumpier than our model suggests.
And that tension leads us straight to the candidates for what those first stars actually were. Let's start with the classic idea. Population 3 stars.
Pop 3. These are the hypothetical first generation of stars, born from truly pristine material.
Just hydrogen and helium from the Big Bang?
That's it. Almost zero metals, which for astronomers is, anything heavier than helium. They would have been gigantic.
Yeah.
And lived very short, very violent lives.
And we should probably clarify the naming because it's so counterintuitive. Our sun is a population-ized star.
Right. Young and metal-rich, about 1.4% metallicity.
So the rule is the lower the metal content, the older the star. Pop 3 are the very first.
A very necessary clarification, yeah. And finding one has been a kind of holy grail.
Yeah.
But we might have the strongest candidate yet, a star cluster called LAP-1b.
Right. And to even see this thing, we needed a bit of a cosmic trick, didn't we?
Oh, absolutely. It's incredibly faint. The light from it was magnified about 100 times by a huge galaxy cluster in front of it.
Gravitational lensing.
A perfect gravitational lens, MACS J0416 to be precise. And when the team analyzed that magnified light, they found it ticked all the boxes for a Pop 3 cluster.
And what were those boxes?
Well, first, it had just trace amounts of metals. Not zero, but extremely low. So it's like the immediate descendant of a pure Pop 3 generation.
Okay.
Second, it formed in a tiny dark matter halo, which is what the theories predict. And third, its total mass is really small, just a few thousand solar masses. All the evidence points to it being a relic of that first metal-poor star formation.
That's incredible. But Pop 3 stars still run on nuclear fusion, like our sun. The other theory for these impossibly bright objects like JGS Z1400 is Well, it's way more out there.
It is, the supermassive dark star. This idea just flips the whole model on its head.
It says the first stars weren't powered by fusion at all.
Right, they were powered by the self-annihilation of dark matter particles, specifically WIMPs.
So dark matter particles crash into each other, they annihilate, and that releases energy that heats the gas.
Exactly. So instead of a tiny, dense fusion core, you get this giant, puffy, bloated cloud of hydrogen and helium that's kept hot and incredibly bright by a dark matter engine at its center.
And the team that studied JWST Z14-0 said its properties actually fit the dark star model. Did they find a smoking gun?
They found a tantalizing clue. JWST Z14-0 and a few other objects, they showed this specific absorption feature in their light, a feature that's a key prediction of the dark star theory.
Okay, but hang on. If dark stars are supposed to form in this pristine, metal-free gas, how can that be true if JWST Z14-0 also shows signs of oxygen? Oxygen is a metal. It had to come from a previous generation of normal stars that died.
And that is the crucial complication. It's where the two theories might have to meet. The oxygen means it's not pristine, so the hypothesis is that maybe a dark star can form inside a more conventional, already existing galaxy.
A second-generation dark star?
Something like that. Or maybe the dark matter heating just dominates the energy output for a while, even if some normal stars are around. The bottom line is JWST is giving us strong candidates for both POP3 and dark stars. The cosmic dawn was probably a lot messier than we thought.
Truly amazing. Okay, let's jump forward 13 billion years and shift focus completely. Let's talk about how galaxies die, right here in the local work.
We're talking about quenching. It's the moment a galaxy stops forming stars. It runs out of gas, basically.
And it goes from being a blue, active spiral galaxy to a red, dead elliptical one.
And for small galaxies, this is almost always murder, not suicide. The environment kills them.
And it turns out Andromeda, M31, is the perfect laboratory for studying this, maybe even better than our own Milky Way.
Oh, for sure. Andromeda is way more massive than the Milky Way, maybe twice as massive. And it's had a much more violent past, with a huge merger a few billion years ago.
So its collection of satellite galaxies is much more diverse, a better sample size.
Exactly. And Hubble has shown us that many of Andromeda's satellites have kept forming stars for a surprisingly long time, much longer than some of our big simulations would predict.
So if the simulations are getting the death dates wrong, we need to look at the murder weapons. What is Andromeda actually doing to them?
The main mechanism is something called ram pressure stripping, RPS.
It sounds violent.
It is. Imagine Andromeda is surrounded by this enormous, hot, but very thin atmosphere. It's circumgalactic medium, or CGM.
Okay.
When a small satellite galaxy plunges through that CGM at high speed, it's like a ferocious headwind that just blows all the cold, star-forming gas right out of the small galaxy.
Like driving through a hurricane with the top down.
A perfect analogy.
Yeah.
But, and this is the nuance of the new simulation show, it struggles to strip out gas that's really clumpy and dense.
So the lumpy gas can protect itself for a while.
It can. It has enough self-gravity to hold on, and that can delay the quenching, buying the galaxy maybe a few billion more years of life.
But it's not the only killer.
No, the other one is always there, tidal stripping. That's just Andromeda's raw gravity. It pulls away dark matter and stars from the satellite's outer edges.
Which weakens the satellite's own gravity.
Exactly. It lowers its potential well, which makes whatever gas is left even easier for ram pressure to strip away. It's a 1-2 punch.
And the sources really emphasize that survival comes down to one thing: mass. There's a clear dividing line.
There is. This is the key insight. Only the most massive satellites, those over about 100 million solar masses, can keep making stars for a long time after falling in towards Andromeda.
And the smaller ones?
Most of them were already dead on arrival. They were quenched before they ever got close to Andromeda's inner regions.
Which is this idea of pre-processing.
Right. Something else killed them first, out in the cosmic suburbs. And for the tiniest, ultra-faint dwarf galaxies, the killer was probably cosmic reionization itself 10 billion years ago.
The same event that the first stars kicked off.
The very same one. The intense radiation from those first big structures just boiled away the gas from these tiny systems. They were dead long before they met Andromeda.
So the sequence of events is really important here. The galaxy stops forming stars first, and only later does it change its shape.
That's one of the biggest takeaways. The quenching happens fast. The transformation from a disk to an elliptical is slow. The fuel runs out, but the car keeps its shape for a while before it gets smashed up.
And we can't leave Andromeda without mentioning the elephant in the room. The biggest mystery that doesn't quite fit the model.
The Great Plane of Satellites.
Yeah, tell us about that.
About half of Andromeda's satellites are all lined up in this bizarrely thin, flat plane, and they're all moving in the same direction.
Which is not what you'd expect.
Not at all. In our standard cold dark matter model, they should fall in from random directions. A structure that coherent and co-moving is. Well, it's very hard to explain. It's a real puzzle.
So from the cosmic dawn to galactic death, all driven by these huge dark matter structures. Now, let's zoom in on one very specific, very strange system that shows us both creation and destruction up close. The Apep system.
Apep is a fantastic find. It's what we call a colliding wind binary. You have two absolutely massive, super hot Wolf-Rayet stars orbiting each other.
And Wolf-Rayet stars are famous for their powerful stellar winds.
Extremely powerful. And where those two winds smash into each other, a shock wave forms.
And that's where the magic happens.
That's where the dust is made. These systems are cosmic dust factories, specifically carbonaceous dust. And JWST gave us this breathtaking image of it.
What did it show?
Luminous dust arranged in 4 perfect nested spirals, like a cosmic pinwheel. It's gorgeous.
And those spirals are like tree rings, right? They tell a story.
They do. Each spiral corresponds to one close approach of the two stars. And by measuring the distance between them, we can tell the orbital period is over 190 years. One of the longest ever seen for a system like this.
But the really new discovery, the thing that makes Apep unique, is that it's not a binary. It's a triple system.
Exactly. There's a third star, a massive O-type supergiant, that's gravitationally bound to the other two.
And what's the third star doing?
It's a wrecker.
A wrecker.
Yeah, as it moves through its own orbit, we can see it carving out a visible cavity in the dust nebula that the other two created. It's actively destroying some of the dust.
So for the first time, we're actually seeing dust destruction by a third star in a system like this.
The very first time. So Apep is this perfect little laboratory. The inner pair are creating the raw materials for future stars and planets.
The carbon dust.
And the third star is processing it, destroying some of it. It's a complete life cycle of heavy elements in one system.
Okay, to bring this whole deep dive together for you, the listener, we've really spanned the entire history of the universe today.
And the main takeaways really center on how these new observations are challenging our standard models. First, the hunt for the universe's first stars now has 2 leading candidates.
You have the classic primordial POP3 stars, fueled by hydrogen.
And you have the radical supermassive dark stars, fueled by dark matter itself. And JWST is finding compelling evidence for both.
And second, here in the present day, we're learning that the death of galaxies is a systematic environmental process. Quenching is fast, happening before the galaxy's shape changes.
And for the smallest galaxies, they were pre-processed, killed off billions of years ago, long before they got anywhere near a big host like Andromeda.
Which brings us to our final thought. The sources make it clear that the very first POP3 stars could only form and survive within the smallest dark matter halos in the early universe.
And today, the death and disruption of satellite galaxies is governed entirely by their journey through the largest dark matter halos we see.
So you have the tiniest dark matter structures birthing the first light.
And the largest dark matter structures extinguishing the last light in small galaxies.
So here's something for you to think about. If we could perfectly understand the physics that governed how those small, early dark matter structures formed, what would that tell us about the ultimate fate of the massive dark matter structures and the galaxies like our own that exist today?
The physics of the beginning and the end. They might be connected by the evolution of dark matter in ways we're only just starting to grasp.